Hi, I'm Tom Dick. I'm a math advisor for Texas Instruments, and this video is part of the TI in Focus AP Calculus series. We're going to be using the TI-84 to calculate some areas and volumes using definite integrals. As an example, we're going to use free response question number 5 from the 2019 AB exam. Let's take a look. Now in that problem, there were two functions given bounding a region. One was labeled g of x, and we've entered it here as our y1, negative 2 plus 3 times the cosine of pi over 2 times x. The second curve, labeled h of x in the problem, we've entered as y2, 6 minus 2 times the quantity x minus 1 squared. Now the region was also bounded between two vertical lines, and I'm going to use those as my x-min and x-max. One vertical line was the y-axis, so that's our x-min equals 0. And the other vertical line was x equal 2, so I've set that as my x-max. Now I'll just set the y-min and y-max to negative 7 to 7, so the region will fit on our screen nicely. Let's take a look at the graph, and there's our region. So the first problem was to actually calculate the area of this region in between those two curves, between 0 and 2. And let's take a look. Let's see, make sure we clearly identify, okay, that bottom curve was our g of x, or our y1, and the upper curve is the h of x, or our y2. So that's the information we need to set up a definite integral to calculate that area. Alright, so I'll go back to the calculation screen. Let's pull up the math menu, and down there at the bottom, number 9 is our integral. And we bring that up, we get the nice integral template. Let's see, our region runs from x equals 0 to x equals 2, and we'll be looking at the upper curve minus the lower curve. That'll be y2 minus y1. So let me retrieve y2 from the y variables menu and subtract y1. Let's retrieve that. And then finally, we'll integrate with respect to x, and this should give us our definite integral value. Let's see, it's actually 14 2/3. Part B of this question was kind of interesting. It said this base of this solid was our region, but it actually explicitly gave us the area of each cross section for each value of x. That area function was just 1 over x plus 3. So to get the volume of that region, we'll just need to integrate that area function from one end to the other. So we'll integrate again from 0 to 2. But now we'll use an integrand that's just the given area function. And again, that area function that they gave us was 1 over the quantity x plus 3. So it was that simple to set up, and now we just integrate with respect to x, and we get the definite integral value of 0.5108 and so forth. Now that's actually equal to the natural log of 5 minus the natural log of 3. Okay, part C of this problem asked us to take this region and rotate it around the horizontal line y equals 6. Be handy for visualization purposes to actually get a horizontal line. So I'm getting that from the draw menu. Horizontal 6 will draw us a nice horizontal line at y equals 6. Alright, this helps us visualize what's going on. So we're taking this region R, going to rotate it around that line. This gives us cross sections that classically are washers. Our outer radius will be from that line y equals 6 all the way down to our y1. So 6 minus y1 will give us that outer radius. And the whole, the inner radius, will be 6 minus y2. That's the information we'll need to set up the definite integral. So let's go back to our calculation screen. Again, get the definite integral. Again, we'll integrate from 0 to 2. And we've got, let's see, circular pieces, the washers, the outer radius. We'll take pi times that radius squared, which was 6 minus y1. So I'll need to retrieve that from the y variables menu again. So 6 minus y1, that quantity squared. So that's giving us the outer area. Now we want to subtract the area of the hole in the washer. So that'll be pi, again, times the inner radius squared. And the inner radius squared would be 6 minus y2. So let's retrieve that. And we've got our inner radius there. We need to square that. And finally, we'll integrate with respect to x. And that was really what was asked for in part C of this problem, was this setup. Now you would want to use g of x and h of x in place of our y1 and y2 here in this integral. Now there's nothing stopping us from going ahead and calculating that. And there we see the value of that volume of that solid revolution. Well, that winds up this short video. For more resources like these, please see education.ti.com.